Hi, my name is Lisa Gerhardt. I work here at NERSC. I'm in the data and analytics division, so I'm on the more user-facing side of things. One of the people who helps the people cause all the problems that you guys are monitoring and defending against. So what I was going to talk to you about today is some of our ideas that we had for developing a data management framework here at NERSC. So for those of you that aren't that familiar with NERSC, NERSC supports the broad science needs of the DOE Office of Science. We don't do any classified computing or any expert-controlled software. It's all open science here. We have about 6,000 users from a wide variety of ranges. All the DOE Offices of Science, so materials science, climate, high-energy physics, astrophysics, they all run here. In any given year, we have about 750 different science projects running at NERSC. So there's a lot of variety and different kind of things going on here. We also support the Joint Genome Institute, which is mainly concerned with doing genome classification and high-energy physics cluster. So there's a wide range of things that run here. We have a lot of science that comes out. We have about 2,000 rough-read publications per year. In 2015, the Nobel Prize in Physics about neutrino oscillation was based on work done at NERSC back in the 2000s. And we have a copy of their raw data in HPSS still. So this is just a quick overview of the NERSC resources that we have. So we have two large HPC computers. Our newest one is Cori. It came online last year. It's a Cray XC40. It's about 30 petaflops. It's got about 9,000 Knights Landing nodes and about 2,000 Haswell nodes, which are just sort of traditional large core Linux machines. It has a 28 petabyte Lustre file system that's attached to it. And this thing is pretty fast, I think pretty fast. It's got a bandwidth of about 700 gigabytes per second aggregate. Cori is sort of unique in that it's aimed at two different workflows. It's aimed at the more traditional HPC workflow and then the data-intensive workflow that you see that's more often associated with physics and genomics kind of things. And we also have Edison, which is, it's a little bit older, so it's a little smaller. It's only 3 petaflops, has an 8 petabyte Lustre file system. So Cori's Lustre Scratch is mounted on Cori and Edison. But they also have the burst buffer, which if you were in the BOF this morning, you heard Dave talk all about. And that's basically intended for super fast I/O. That's mounted only on Cori. It's about 2 petabytes of capacity, has about 2 terabytes aggregate bandwidth. So it's intended for bursty I/O that's happening while computing. And then we have our Spectrum Scale file system. It's about 7 petabytes. This is intended for medium-term storage of data and for sharing scientific data. So groups will put data that they need to share amongst other members of the group on this file system. And then we also have a tape HPSS archive, which Kirill told you about this morning. Has about 100 petabytes of data on it. We have data back from, 1970 in there?
40 years.
40 years, yeah.
What, can you read the tape from 40 years?
We can read the tape. They can't read the data usually, but...
We had an interesting request, actually.
Yeah. Yeah, it was, we were pulling a file off from 1980, user trying to unpack the binary. It was very interesting. So, like I mentioned before, we're slightly different from other DOE centers in that data-intensive workloads are a significant portion of our workload here at NERSC. So we just did a survey during the last the last call for projects, and more than a third of the projects identified themselves as either working directly with experimental data or making simulations derived from experimental data. So it's a fairly large portion of our workflow is doing data-intensive stuff with high I/O, lots of spamming the file system. And these groups are seeing an increasingly larger burden of moving and managing the data. What we see with these groups is that they'll come in and they'll create again and again the same sorts of frameworks for managing their data and for moving things around. So this is definitely a growing need. They're having trouble finding their files. They're having trouble understanding what those files are when they find them. And they're having trouble moving data between the layers of the system. And then we have a lot of really data-centric workflows that need to trigger when data arrives and do a bunch of things. And then we have some plots of the growth of the size of our file systems over the years, just to give you an idea. So the one on the left is project. That we constrain with quotas. So the growth hasn't taken off quite as exponentially as you see with HPSS, where it's essentially unconstrained. And so we're even with the quotas, though, we're still rising. We've gone up 2 petabytes in 2 years. So we have a fairly lively file system here. So I mentioned Cori Scratch has 30 petabytes capacity. We fired it up last year. The users have already filled up 13 petabytes of data. We got 1.2 billion inodes on there. If you look at sort of an average day, you see about 18 million files are modified, and about half a petabyte of data is read and written from our Scratch file system. And the intention of the Scratch file system is this is to catch I/O during computing. We have user-based directories on there, so we don't have any group quotas. It's just user-based. And it's because of economic reasons, we manage this with a purge. So if your data isn't read within 8 weeks, it'll be automatically removed from the system. So the idea is people come on, they compute, they dump their data goes in and out of Scratch. When they're done with their campaign of computing, it moves down either to project if they think they're going to use it again, or to HPSS if they think they're really not going to need it in the near future. And you can sort of see this is sort of the general way that data moves around our center. The thick lines mostly sort of following the hierarchy of the file system. It goes from the fast to the medium-term storage down to HPSS. But you do see folks that move data directly from HPSS to Scratch because they're at their quotas in project or some other reason. So project is sort of our shared resource in the center. It's intended for science groups to share their data. It sees a lot less churn. So we have 6 petabytes, a little under 1 billion inodes, but the fluctuation in number of files per day is only about 1 million. So it's not as crazy, but data lives on there a lot longer. And you'll see experimental groups will come back and re-access their data as long as 2 years after they put it on the center. So it stays active for a long time. And then our HPSS system, the data increases on there at a rate of about 30 terabytes a day. So to manage all this churn and to move all this stuff all around, our users basically have the traditional Linux tools, ls, find, and du. That's it. And movement between the tiers is copy, move, and for HSI, for HPSS, you have HSI and HTAR. So it's a pretty limited repertoire.
Is project the GPFS cluster?
Yeah. Yeah.
But they don't use any of the GPFS tools for quota or usage?
So we manage quota with the GPFS, but that's pretty much it that we expose to the users. Okay. So this is I'm just going to run through 2 science examples to give you sort of an idea of what the typical groups are doing here at NERSC. So the first one is the Majorana group. They're basically looking for neutrinos, a special decay of neutrinos that will indicate whether a neutrino is its own antiparticle, whether it's a Majorana particle. And they have this little apparatus here. It's this little thing right here. It's a bunch of crystals. They're the size of like a human torso. They're at the University of Washington. This is a group that has about 60 users. And experimental data from this is kept at UW, and then it's mirrored here at NERSC. So they transfer it with Globus, and it hits our project file system. And they have this, this kind of directory structure where it's broken down per year, and inside is a month, and then their data files go in there. And when the month ends, they run this little script that bundles this thing up and puts a copy into HPSS. But this Globus transfer has some problems. The files trickle in they straggle in over a long time period. And so you can have put this directory into HPSS, and then you get another file that shows up in March, even though March is already done. And so they didn't want to re-aggregate this whole thing and put it back into HPSS. So instead they wrote this script that does a find and does it like a supplemental tarball. And that was like a work of about a week for someone to put together. But it has problems. Like during the switch to daylight savings time, they missed a bunch of files because they didn't account for that. So things like that happen. It takes a lot of maintenance to keep up on. And then the other problem that they run into is in the project directory. The project directory is created as a shared area. It's group readable, but permissions drift. Users come on with a UMask set in such a way or something. Suddenly parts of it become no longer group readable. And so when that happens and they hit their quota, and the PI, the head of the project, hops on there and tries to do a DU, he can't see 30% of his project directory because the permissions have drifted. And the only recourse he has is to open a ticket and ask the friendly admins to give him a report. So that's that's how a small group with sort of basic tools runs. An example of a much more sophisticated data flow is the advanced light source. If any of you stayed up at the guest house, it's this round building up there. And basically, it's a bunch of super accelerated electrons that they use to generate high energy photons that they can use to image a variety of different materials. They run 24/7. People bring in their samples, they take their data, and they go back home. So these scientists, they don't want to have to do anything with processing the data. They just want their finished results that come out. And if they can get them as close to as real time as possible, that's even better. So they have a very sophisticated thing called the Spot Suite, which basically on the ALS end, it bundles the imaging data up with some metadata into HDF5. It moves it via ESNet directly into our project file system. Then there's a whole bunch of watchers that watch these directories. And when the files come in, they have a Mongo database that coordinates everything. When a file comes in, they put a copy into HPSS. Then they submit a bunch of analysis jobs to Corey and Edison. You get some final derived data out. And then when that hits, that also is put into HPSS. And then an even smaller thumbnail is generated that's shown on this web page. And then the users can come on and download whatever data they need via this web portal. So they have this whole, and then when they run out of room on their project, in their project quota, which happens fairly often, they have special purge scripts that they run. And it's I think, easily probably about 10,000 lines of code that are doing all this management that they've written. So we're looking at how we can help these groups, new groups that come in, and existing groups with their issues with managing data. So this framework that we're thinking about should be able to help users find their data. It should be able to help them move their data. It should be able to help them trigger their workflows. And ultimately, it should be able to deliver some kind of metadata tracking. And it needs to do all this without impacting the file system performance. And ideally, we'd like to avoid a really heavy third-party software because people run at all different sites. And if they have to learn something that makes NERSC a special snowflake, it makes it less desirable. So we're looking at ways we can leverage the existing file system tools like ILM, Robinhood, and GUI to try and help the users move their data throughout the center. So as a first step, we built something that we call the data dashboard. And the idea is that eventually this would serve as the central coordinating point for all the other tools. And we went for addressing a really common issue that comes up a lot, which is dealing with the shared project space, hitting the quota, and permissions drifting. So this is fed by daily ILM scans. So it takes about 4 hours to scan our 6 petabyte project file system. Once that scan is finished, it's about a 200 gigabyte text file. We take this and parse it with Spark to generate various aggregates that we would report to the user, this is pretty fast. It takes about 5 minutes on 16 nodes. And then we use the D3 JavaScript library to show render the GUI for the user to look at. So the nice thing is that the entire process from starting the scan at midnight to displaying only takes a few hours. And the longest part is really the scan. So now I'm going to see if I can loop over and just do a quick show of, I'll do a live demo. Let's hope it works. Okay, yeah, you can see it? Great. Okay, so this is, so normally you hit this page, you have to log in with your NERSC credential. I figured you guys didn't want to see that, so I pre-logged in. So this is what you see when you log in. So these are all of the directories. These are file sets on the project file system that you see that you're a member of. So if you're in the Alice group, you automatically can see this directory. And so the first thing it gives you is just a visual representation of where you are relative to your quota. So this is your space quota. Here's your inode quota. We have groups that fill up either one of these over and over again. And so you get just a quick view of how your file systems are doing as soon as you log in. And you know which one is trouble. most people would only see one or two of these. I'm in staff, so I see a bunch of these. And so
File sets or just directories?
these are directories and file sets. So we have, the way we have it set up, each project has its own directory that's a file set. So if we scroll down to this MPCCC right here, that's the staff, the one that all of NERSC staff shares. So when this fills up, it generates a lot of excitement. So if this does fill up, you can come on here and toggle the usage details. And it gives you right away a breakdown by user. And embarrassingly, I'm the largest user on the system. So then if you're the one managing this, you can go and say, hey, Lisa, clean up your stuff, because no one can work. And then we also have some new functionality where if I'm coming on here as a user and I say, I need to clean up, where should I start? Oh no, let's see if this works. It'll give you a breakdown of your files and directories based on the largest size, and it doesn't seem like it's coming. Okay. But I anticipated this and took a screen cap. So this is what you see. So then you can look at this and you can say, hey, I've got a 2 terabyte blob.txt in my directory. Maybe that's a good place to start if I'm going to archive this stuff. And then you can also look at it relative to access time. So you can say, hey, I haven't looked at this in 3 years. Maybe I can put that in HPSS. And so that's sort of a first start.
And this is aggregated on a daily basis? You see these are updated?
Yeah, yeah. And it actually says right there, it tells you what time the scan finished.
I see.
So you can know that, if you go and aggregate, if you go and put that into HPSS, you can know it's not going to update, so users aren't confused. So that's kind of where we are right now. Let's see if this is going to come back up. So the next step that we're looking at for the data dashboard, at least, is to expand this to showing data from Lustre and HPSS. And our users particularly interested in getting data out of Lustre, in part so that they can avoid or be notified when they're about to lose data from the purge. This is somewhat challenging because, at least at NERSC, the Lustre tools can't keep up with the file system usage. And when they fall too far behind, we've even had them crash the file system, which is really not what you want out of a monitoring system. And then HPSS hasn't really been designed with the idea of sort of generating fast reports about its data. So it's not really clear how we're going to get information out of there, but that's our next steps, is to look at this. And the other thing we're looking at is a tool for the project leads to be able to fix drifted permissions. We'd like to set up an ILM policy that'll just come every night and enforce group readable on the directories. And then further on, we're working on functionality for users to be able to walk their file system via the GUI. And looking much longer term, we're thinking about better ways to help users move data throughout the system. Ideally, what we'd like is to be able to automate a set of rules for when let's say a new file has appeared or it hasn't been read for 6 months. You can automatically migrate that to HPSS. Or when data is finished, when it appears in Scratch, you can make a copy and put it into the GPFS system. So we're looking at ways that we can leverage AFM and Robinhood to try and implement this. And then Kirill told you about our test implementation of GI that we're working on. And extending that even further, what would be really nice is to be able to add hooks for user workflow support. So in the same way that you can trigger system level commands to move things around, to put a little hook in there so that users could run their own created directory, their own created scripts when data hits the system. Then you could imagine a file comes in, it'll fire off a script that updates the database, submits a bunch of jobs, sends an email, does all that stuff without them sitting here having to continuously find on their directories. And then much longer term, we're thinking about ways that you could use the extended attributes to try and put metadata in with your files and have them move around the system. So just to conclude, we're working on a framework to try and help the users move their data throughout the center. I think that these file systems are fairly common, and this is a problem that occurs again and again and again. So if anyone else is working on this or is interested in this, please let me know. Let's work together. I'm sure we probably all have some tools we can put together and get some good stuff out. And I think this is critical in the future as data volumes increase. So, thanks.
Thanks, Lisa.